Third, the equations of Poisson and Laplace. There is still a third way of expressing the law of the inverse square, and this can be deduced most readily from Gauss' theorem. Let us examine the small rectangular parallel epipede of volume dx, dy, dz, which is bounded by the six-plane fx equals plus and minus 1/2 ddx, y equals eta plus and minus 1/2 dy, z equals zeta plus and minus 1/2 dz. We shall suppose that this element does not contain any point charges of electricity or part of any charged surface. But for the sake of generality, we shall suppose that the whole space is charged with a continuous distribution of electricity, the volume density of electrification in the neighborhood of the small element under consideration being rho. The whole charge contained by the element of volume is accordingly rho multiplied by dx multiplied by dy multiplied by dz, so that Gauss's theorem assumes the form integral of normal component of the electric field over the surface ds equals 4 pi rho multiplied by dx multiplied by dy multiplied by dz. The surface integral is the sum of 6 contributions, one from each face of the parallelepiped. The contribution from that face, which lies in the plane x, equals xi minus 1/2 dx is equal to dy multiplied by dz, the area of the face, multiplied by the mean value of the normal component of the electric field over this face. To a sufficient approximation, this may be supposed to be the value of the normal component of the electric field at the center of the face, that is, at the point xi minus 1/2 dx, eta, zeta, and this again may be written normal component of the electric field at xi minus 1/2 dx, eta, zeta. So that the contribution to the integral of normal component of the electric field over the surface ds from this face is normal component of the electric field at xi minus 1/2 dx eta zeta multiplied by dy multiplied by dz. Similarly, the contribution from the opposite face is normal component of the electric field at xi plus 1/2 dx eta zeta multiplied by dy multiplied by dz, the sign being different because the outward normal is now the positive axis of x, whereas formerly it was the negative axis. The sum of the contributions from the two faces perpendicular to the axis of x is therefore normal component of the electric field at xi plus 1/2 dx eta zeta minus normal component of the electric field at xi minus 1/2 dx eta zeta multiplied by dy multiplied by dz. The expression inside curled brackets is the increment in the function normal component of the electric field when x undergoes a small increment, dx. This we know is dx multiplied by partial derivative of normal component of the electric field with respect to x. So that expression can be put in the form partial derivative of normal component of the electric field with respect to x multiplied by dx multiplied by dy multiplied by dz. The whole value of the integral of normal component of the electric field over the surface ds is accordingly partial derivative of normal component of the electric field with respect to x plus partial derivative of normal component of the electric field with respect to y plus partial derivative of normal component of the electric field with respect to z, the whole multiplied by dx multiplied by dy multiplied by dz, and the equation now assumes the form partial derivative of normal component of the electric field with respect to x plus partial derivative of normal component of the electric field with respect to y plus partial derivative of normal component of the electric field with respect to z equals 4 pi rho. This is known as Poisson's equation. Clearly, if we know the value of the potential at every point, it enables us to find the charges by which this potential is produced. 50th. In free space where there are no electric charges, the equation assumes the form partial derivative squared of potential with respect to x squared plus partial derivative squared of potential with respect to y squared plus partial derivative squared of potential with respect to z squared equals 0. And this is known as Laplace's equation. We shall denote the operator partial derivative squared with respect to x squared plus partial derivative squared with respect to y squared plus partial derivative squared with respect to z squared by the Laplacian operator, so that Laplace's equation may be written in the abbreviated form Laplacian of potential equals 0. Equations expressing Poisson's equation and Laplace's equation express the same fact as Gauss's theorem, but express it in the form of a differential equation. Laplace's equation shows that in a region in which no charges exist, the potential satisfies a differential equation which is independent of the charges outside this region by which the potential is produced. It will easily be verified by direct differentiation that the value of the potential given in a previous equation is a solution of Laplace's equation. We can obtain an idea of the physical meaning of this differential equation as follows. Let us take any point and construct a sphere of radius r about this point. The mean value of the potential averaged over the surface of the sphere is equal to the integral of the potential over the sphere divided by the surface area of the sphere, where r and the angles theta and phi are polar coordinates, having the origin as their reference point. If we change the radius of this sphere from r to r plus dr, the rate of change of the mean value of the potential with respect to r is given by the integral over the sphere of the partial derivative of the potential with respect to r divided by 4 pi r squared, and this is equal to 0 by Gauss's theorem, showing that the potential is independent of the radius r of the sphere. Taking r equals 0, the value of the potential is seen to be equal to the potential at the origin. This gives the following interpretation of the differential equation. The potential varies from point to point in such a way that the average value of the potential taken over any sphere surrounding any point is equal to the value of the potential at the center of that sphere. 51st. Theorem. The potential cannot have a maximum or a minimum value at any point in space which is not occupied by an electric charge. For if the potential is to be a maximum at any point 0, the potential at every point on a sphere of small radius r surrounding 0 must be less than that at 0. Hence, the average value of the potential on a small sphere surrounding 0 must be less than the value at 0, a result in opposition to that of the last section. A similar proof shows that the value of the potential cannot be a minimum. 52nd. A second proof of this theorem is obtained at once from Laplace's equation. Regarding the potential simply as a function of x, y, and z, a necessary condition for the potential to have a maximum value at any point is that the second partial derivative of the potential with respect to x, the second partial derivative of the potential with respect to y, and the second partial derivative of the potential with respect to z shall each be negative at the point in question, a condition which is inconsistent with Laplace's equation. So also, for the potential to be a minimum, the three differential coefficients would have to be all positive, and this again would be inconsistent with Laplace's equation. 53rd. If the potential is a maximum at any point 0, which as we have just seen must be occupied by an electric charge, then the value of the outward normal derivative of the potential must be negative as we cross a sphere of small radius r. Thus, the surface integral of the outward normal derivative of the potential over a small sphere surrounding 0 is negative. Where the integration is taken over a small sphere surrounding 0, and by Gauss's theorem the value of the surface integral is negative 4 pi e, where e is the total charge inside the sphere. Thus, e must be positive, and similarly if the potential is a minimum, e must be negative. Thus, if the potential is a maximum at any point, the point must be occupied by a positive charge, and if the potential is a minimum at any point, the point must be occupied by a negative charge. 54th, we have seen in section 36 that in moving along a line of force, we are moving at every point from higher to lower potential, so that the potential continually decreases as we move along a line of force. Hence, a line of force can end only at a point at which the potential is a minimum, and similarly, by tracing a line of force backwards, we see that it can begin only at a point at which the potential is a maximum. Combining this result with that of the previous theorem, it follows that lines of force can begin only on positive charges and can end only on negative charges. It is of course possible for a line of force to begin on a positive charge and go to infinity, the potential decreasing all the way, in which case the line of force has, strictly speaking, no end at all. So also, a line of force may come from infinity and end on a negative charge. Obviously, a line of force cannot begin and end on the same conductor, for if it did so, the potential at its two ends would be the same. Hence, there can be no lines of force in the interior of a hollow conductor which contains no charges. Consequently, there can be no charges on its inner surface. Fifth, let us select any small area ds in the field and let us draw the lines of force through every point of the boundary of this small area. If ds is taken sufficiently small, we can suppose the electric intensity to be the same in magnitude and direction at every point of ds, so that the directions of the lines of force at all the points on the boundary will be approximately all parallel. By drawing the lines of force, points on the boundary will be approximately all parallel. By drawing the lines of force, then, we shall obtain a tubular surface, that is, a surface such that in the neighborhood of any point, the surface may be regarded as cylindrical. The surface obtained in this way is called a tube of force. A normal cross-section of a tube of force is a section which cuts all the lines of force through its boundary at right angles. It therefore forms part of an equipotential surface. 56th theorem. If omega 1 and omega 2 be the areas of two normal cross-sections of the same tube of force, and R1 and R2 the intensities at these sections, then consider the closed surface formed by the two cross-sections of areas omega 1 and omega 2, and of the part of the tube of force joining them. There is no charge inside this surface, so that by Gauss's theorem, the integral of the normal component of the electric field over the surface is equal to 0. If the direction of the lines of force is from omega 1 to omega 2, then the outward normal intensity over omega 2 is R2, so that the contribution from this area to the surface integral is R2 multiplied by omega 2. So also over omega 1, the outward normal intensity is negative R1, so that omega 1 gives a contribution of negative R1 multiplied by omega 1. Over the rest of the surface, the outward normal is perpendicular to the electric intensity, so that the normal component of the field is equal to 0, and this part of the surface contributes nothing to the integral. The whole value of this integral then is R2 multiplied by omega 2 minus R1 multiplied by omega 1, and since this, as we have seen, must vanish, the theorem is proved. 57th. Coulomb's law. If R is the outward intensity at a point just outside a conductor, then R is equal to 4 pi sigma, where sigma is the surface density of electrification on the conductor. We have already seen that the whole electrification of a conductor must reside on the surface. Therefore, we no longer deal with a volume density of electrification rho, such that the charge in the element of volume dx multiplied by dy multiplied by dz is rho multiplied by dx multiplied by dy multiplied by dz, but with a surface density of electrification sigma, such that the charge on an element ds of the surface of the conductor is sigma multiplied by ds. The surface of the conductor, as we have seen, is an equipotential, so that by a previous theorem, the intensity is in a direction normal to the surface. Let us draw perpendiculars to the surface at every point on the boundary of a small element of area ds, these perpendiculars each extending a small distance into the conductor in one direction, and a small distance away from the conductor in the other direction. We can close the cylindrical surface so formed by two small plane areas, each equal and parallel to the original element of area ds. Let us now apply Gauss's theorem to this closed surface. The normal intensity is 0 over every part of this surface, except over the cap of area ds, which is outside the conductor. Over this cap, the outward normal intensity is R, so that the value of the surface integral of normal intensity taken over the closed surface consists of the single term R multiplied by ds. The total charge inside the surface is sigma multiplied by ds, so that by Gauss's theorem, R multiplied by ds equals 4 pi sigma multiplied by ds, and Coulomb's law follows on dividing by ds. 58th. Let us draw the complete tube of force, which is formed by the lines of force starting from points on the boundary of the element ds of the surface of the conductor. Let us suppose that the surface density on this element is positive, so that the area ds forms the normal cross-section at the positive end, or beginning of the tube of force. Let us suppose that at the negative end of the tube of force, the normal cross-section is ds prime, that the surface density of electrification is sigma prime being of course negative, and that the intensity in the direction of the lines of force is r prime. Then, as in the previous equation, r prime multiplied by ds prime equals negative 4 pi sigma prime multiplied by ds prime, since the outward intensity is now negative r prime. Since r and r prime are the intensities at 2 points in the same tube of force at which the normal cross-sections are ds and ds prime, it follows from the theorem that r multiplied by ds equals r prime multiplied by ds prime, and hence, on comparing the values just found for r multiplied by ds and r prime multiplied by ds prime, that sigma multiplied by ds equals negative sigma prime multiplied by ds prime. Since sigma multiplied by ds and sigma prime multiplied by ds prime are respectively the charges of electricity from which the tube begins and on which it terminates, we see that the negative charge of electricity on which a tube of force terminates is numerically equal to the positive charge from which it starts. If we close the ends of the tube of force by two small caps inside the conductors, we have a closed surface such that the normal intensity vanishes at every point. Thus, by Gauss' theorem, the total charge inside must vanish, giving the result at once. Fifty-ninth. The numerical value of either of the charges at the ends of a tube of force may conveniently be spoken of as the strength of the tube. A tube of unit strength is spoken of by many writers as a unit tube of force. The strength of a tube of force is sigma multiplied by ds in the notation already used, and this, by Coulomb's law, is equal to 4 pi multiplied by r multiplied by ds, where r is the intensity at the end ds. Where r is the intensity at the end. The theorem of section 56, r multiplied by ds is equal to r1 multiplied by omega 1, where r1 and omega 1 are the intensity and cross-section at any point of the tube. Hence, r1 multiplied by omega 1 is equal to 4 pi times the strength of the tube. It follows that the intensity at any point is equal to 4 pi times the aggregate strength per unit area of the tubes, which cross a plane drawn at right angles to the direction of the intensity. In terms of unit tubes of force, we may say that the intensity is 4 pi times the number of unit tubes per unit area which cross a plane drawn at right angles to the intensity. The conception of tubes of force is due to Faraday. Indeed, it formed almost his only instrument for picturing to himself the phenomena of the electric field. It will be found that a number of theorems connected with the electric field become almost obvious when interpreted with the help of the conception of tubes of force. For instance, we proved in an earlier section that when a number of charged bodies are placed inside a hollow conductor, they induce on its inner surface a charge equal and opposite to the sum of all their charges. This may now be regarded as a special case of the obvious theorem that the total charge associated with the beginnings and terminations of any number of tubes of force, none of which pass to infinity, must be zero. 60th. It will be of advantage to study a few particular fields of electric force by means of drawing their lines of force and equipotential surfaces. First, two equal point charges. 61st. Let E1 and E2 be two equal point charges, say at the points x equals negative a and x equals positive a. The equations of the lines of force which are in the plane of x and y are easily found to be partial derivative of potential with respect to x equals partial derivative of potential with respect to y. This equation admits of integration in the form x plus a divided by x minus a plus y plus b divided by y minus b equals constant. From this equation, the lines of force can be drawn and will be found to lie as in the figure. 62nd. There are, however, only a few cases in which the differential equations of the lines of force can be integrated, and it is frequently simplest to obtain the properties of the lines of force directly from the differential equation. The following treatment illustrates the method of treating lines of force without integrating the differential equation. From the equation of the field, we see that obvious lines of force are first y equals 0 and x equals 0, giving the axis AB, and second, x equals 0, and the distances to the charges E1 and E2 are equal, giving the line which bisects the segment AB at right angles. These lines intersect at C, the middle point of a B. At this point, the field has two values, and since the derivative of the potential with respect to x is equal to the derivative of the potential with respect to y, it follows that we must have the x component of the field equal to 0 and the y component of the field equal to 0. In other words, the point C is a point of equilibrium, as is otherwise obvious. The same result can be seen in another way. If we start from A and draw a small tube surrounding the line AB, it is clear that the cross-section of the tube, no matter how small it was initially, will have become infinite by the time it reaches the plane which bisects a B at right angles. In fact, the cross-section is identical with the infinite plane. Since the product of the cross-section and the normal intensity is constant throughout a tube, it follows that at the point C, the intensity must vanish. At a great distance r from the points A and B, the fraction of the difference of the distances to the two charges divided by the sum of the distances to the two charges vanishes to the order of 1 divided by r squared, so that except for terms of the order of 1 divided by r squared, the field at infinity becomes asymptotic to straight lines passing through the origin. Let us suppose that a line of force starts from a making an angle theta with the extended line AB and is asymptotic at infinity to a line through C which makes an angle phi with the extended line AB. By rotating this line of force about the axis AB, we obtain a surface which may be regarded as the boundary of a bundle of tubes of force. This surface cuts off an area of 2 pi times 1 minus cosine of theta multiplied by r squared from a small sphere of radius r drawn about A, and at every point of this sphere, the intensity is E divided by r squared, normal to the sphere. The surface again cuts off an area of 2 pi times 1 minus cosine of phi, multiplied by r squared from a sphere of very great radius r drawn about C, and at every point of this sphere, the intensity is 2E divided by r squared. Hence, applying Gauss's theorem to the part of the field enclosed by the two spheres of radii r and the surface formed by the revolution of the line of force about a B, we obtain the equation 2 pi times 1 minus cosine of theta multiplied by r squared times E divided by r squared minus 2 pi times 1 minus cosine of phi multiplied by r squared times 2E divided by r squared equals 0, from which follows the relation sine of 1/2 phi equals square root of 2 multiplied by sine of 1/2 theta. In particular, the line of force which leaves E in a direction perpendicular to a B is bent through an angle of 30 degrees before it reaches its asymptote at infinity. The sections of the equipotentials made by the plane of x and y for this case are shown in the figure, which is drawn on the same scale as the previous figure. The equations of these curves are, of course, the sum of the reciprocals of the distances to the two charges equals constant. These curves are of the 6th degree. The equipotential which passes through C is of interest, as it intersects itself at the point C. This is a necessary consequence of the fact that C is a point of equilibrium. Indeed, the conditions for a point of equilibrium, namely that the partial derivative of the potential with respect to x is 0, the partial derivative of the potential with respect to y is 0, and the partial derivative of the potential with respect to z is 0, may be interpreted as the condition that the equipotential through the point should have a double tangent plane or a tangent cone at the point. 63rd. Let charges positive E and negative E be at the points x equals positive A and x equals negative A, labeled A and B respectively. The differential equations of the lines of force are found to be partial derivative of y with respect to x equals y divided by x multiplied by the difference of the squares of the distances from the two charges divided by the sum of the squares of the distances from the two charges. The integral of this equation is x plus a divided by x minus a equals constant. The lines of force are shown in the corresponding figure. 64th. Electric doublet. An important case occurs when we have two large charges positive E and negative E equal and opposite in sign at a small distance apart. Taking Cartesian coordinates, let us suppose we have the charge positive E at A0 and the charge negative E at negative A 0, 0, so that the distance between the charges is 2a. The potential is given by E divided by the square root of x minus a squared plus y squared plus z squared, plus E divided by the square root of x plus a squared plus y squared plus z squared. When a is very small, so that squares and higher powers of a may be neglected, this becomes 2eax divided by x squared plus y squared plus z squared. If a is made to vanish, while e becomes infinite in such a way that 2ea retains the finite value mu, the system is described as an electric doublet of strength mu, having for its direction the positive axis of x. its potential is mu x divided by x squared plus y squared plus z squared. Or, if we turn to polar coordinates and write x equals r cosine theta, the potential is mu cosine theta divided by r squared. The lines of force are shown in the corresponding figure. Obviously, the lines at the center of this figure become identical with those shown in the previous figure if the latter are shrunk indefinitely in size. 65th. Point charges positive 4e and negative e. The figure represents the distribution of the lines of force when the electric field is produced by 2 point charges, positive 4e at point A and negative e at point B. At infinity, the resultant force will be 3e divided by r squared, where r is the distance from a point near to A and B. The direction of this force is outwards. Thus, no lines of force can arrive at B from infinity, so that all the lines of force which enter B must come from A. The remaining lines of force from A go to infinity. The tubes of force from A to B form a bundle of aggregate strength E, while those from A to infinity have aggregate strength 3E. The two bundles of tubes of force are separated by the lines of force through point C. At C, the direction of the resultant force is clearly indeterminate, so that C is a point of equilibrium. As the condition that C is a point of equilibrium, we have the absolute value of charge divided by the square of the distance to C from equals the absolute value of charge divided by the square of the distance to C from B, so that AB equals BC. At C, the two lines of force from a coalesce and then separate out into two distinct lines of force, one from C to B and the other from C to infinity in the direction opposite to GB. The equipotentials in this field, the system of curves given by the sum of the reciprocals of the distances to the two charges equals constant, are represented in the corresponding figure, which is drawn on the same scale as the previous figure. Since C is a point of equilibrium, the equipotential through the point C must of course cut itself at C. At C, the potential is 4e divided by the distance from C to a minus e divided by the distance from C to B, which simplifies to e divided by the distance from A to B, since the distance from C to A equals twice the distance from C to B. From the loop of this equipotential which surrounds B, the potential must fall continuously to negative infinity as we approach B, since, by the theorem of section 51, there can be no maxima or minima of potential between this loop and the point B. Also, no equipotential can intersect itself since there are obviously no points of equilibrium except C. One of the intermediate equipotentials is of special interest, namely that over which the potential is zero. This is the locus of the point P given by the difference of the reciprocals of the distances to the two charges being equal to zero, and is therefore a sphere. This is represented by the outer of the two closed curves which surround B in the figure. In the same way, we see that the other loop of the equipotential through C must be occupied by equipotentials for which the potential rises steadily to the value positive infinity at A. So, also, outside the equipotential through C, the potential falls steadily to the value 0 at infinity. Thus, the zero equipotential consists of two spheres, the sphere at infinity and the sphere surrounding B, which has already been mentioned. 66th. As a further example, we may examine the disposition of equipotentials when the field is produced by 3-point charges at the corners of an equilateral triangle. The intersection of these by the plane in which the charges lie is represented in the corresponding figure, in which A, B, and C are the points at which the charges are placed, and D is the center of the triangle ABC. It will be found that there are 3 points of equilibrium, one on each of the lines A, B, D, and CD. Taking the distance AD as A, the distance of each point of equilibrium from D is just less than 1 times A. The same Hooke potential passes through all 3 points of equilibrium. If the charge at each of the points A, B, and C is taken to be unity, this equipotential has a potential of approximately 3.04 divided by A. The equipotential has 3 loops surrounding the points A, B, and C. In each of these loops, the equipotentials are closed curves, which finally reduce to small circles surrounding the points A, B, and C. The drawn equipotentials correspond to the potentials 3.04 divided by A, 3.25 divided by A, 3.5 divided by A, 3.75 divided by A, and 4 divided by A. Outside the equipotential to 3.04 divided by A, The equipotentials are closed curves surrounding the former equipotential, and finally reducing to circles at infinity. The drawn curves correspond to the potentials 2 divided by A, 2.25 divided by A, 2.5 divided by A, and 2.75 divided by A. There remains the region between the point D and the equipotential 3.04 divided by A. At D, the potential is 3.04 divided by A, so that the potential falls as we recede from the equipotential and reaches its minimum value at D. The potential at D is, of course, not a minimum for all directions in space, for the potential increases as we move away from D in directions which are in the plane ABC, but obviously decreases as we move away from D in a direction perpendicular to this plane. Taking D as the origin and the plane ABC as the plane of x and y, it will be found that near D, the potential is given by 3 divided by a plus 3 divided by 4, a squared, multiplied by the quantity x squared plus y squared minus 2z squared. Thus, the equipotential through D is shaped like a right circular cone in the immediate neighborhood of the point D. From the equation just found, it is obvious that near D, the sections of the equipotentials by the plane ABC will be circles surrounding D. From a study of the section of the equipotentials as shown in the corresponding figure, it is easy to construct the complete surfaces. We see that each equipotential for which the potential has a very high value consists of 3 small spheres surrounding the points A, B, and C. For smaller values of the potential, which must, however, be greater than 3.04 divided by A, each equipotential still consists of 3 closed surfaces surrounding A, B, and C, but these surfaces are no longer spherical, each one bulging out towards the point D. As the potential decreases, the surfaces continue to expand until, when the potential reaches 3.04 divided by A, the surfaces touch one another simultaneously, in a way which will readily be understood on examining the section of this equipotential as shown in the corresponding figure. It will be seen that this equipotential is shaped like a flower of 3 petals from which the center has been cut away. As the potential decreases further, the surfaces continue to swell, and when the potential equals 3 divided by A, the space at the center becomes filled up. For still smaller values of the potential, the equipotentials are closed, simply connected surfaces, which finally become spheres at infinity corresponding to the potential equal to 0. The sections of the equipotentials by a plane through the line dA perpendicular to the plane ABC are shown in the corresponding figure.